this section we learn something new, right? Exciting?
Yeah.
Yeah. Called imaginary numbers. Personally, I don't like the fact that mathematicians, when they founded imaginary numbers, decided to call it imaginary, because it makes you think of unicorns and things that don't exist. And imaginary numbers are actually numbers. But let me maybe explain why they even decided to create imaginary numbers. Up until now, if you had the square root of negative 25, and I asked you what the square root was, there's not two numbers multiplied together that are negative, right? A positive times a positive is a negative times a negative is a positive, a negative times a negative is a positive. So the same exact two numbers, doesn't matter what I do, if I multiply them together, it's still a positive number, it's not negative. Okay, so right now you would say it does not exist. So the problem is that this eventually will be a solution to a quadratic. And I'm just going to maybe explain a little bit. This is going to be nothing in this section, but something that's going to come up later in the class. But I want to show you why negative numbers, the square root of negative numbers, it's important that we still treat them as a number. When we graph a quadratic, it's always in the shape of a U. Okay, we're not on the graphing chapter, I know that. We're going to get that next. But when we graph a quadratic, it's always in the shape of a U. Just like when we graph absolute value, it's always in the shape of a V. So anytime you see a quadratic, all of the quadratics you've been dealing with, any of those that have the largest exponent is a 2, it's called a quadratic. It's always going to give you a parabola when you graph it. Always. Okay? We've been solving quadratics, and when we solve quadratics, we end up with two solutions. Right? That's why we have the plus or minus, and that's why I always say there's always two solutions. Okay, those solutions are called roots. They're called zeros. They're called solutions. All of those are synonymous. And the zero really is where the parabola crosses the x-axis. So all the factoring you've been doing and you've been solving, if you had a quadratic in standard form, x squared plus 5x plus 4, you factored it to x plus 4, x plus 1, and then you solve it, x equals negative 4, x equals negative 1. That's what we've been doing, right? That tells me that at negative 4 and negative 1, the parabola that is represented by that expression crosses the x-axis at those two numbers. That's why we solve it, because we want to figure out where it crosses the x-axis. So those are called roots, solutions, zeros. Okay? Other parabolas may only cross the x-axis at one point. Well, I thought there were two solutions to quadratics. How can it just be one point? Well, remember when you factored x minus 2 times x minus 2 and solved? You got x equals 2 twice. It was the same answer, but we called it a double root. Okay? It's still two solutions, but it's just the same number twice. It's a double root. When you get a double root, what happens is instead of the curve going through the x-axis at that point, it goes to the x-axis at that point and bounces back up. That's what happens with a double root. Double root is where it bounces off the x-axis. A single root is where it goes through the x-axis. Okay? And the final kind of parabola that we might have with quadratics might look like this. Where does it go through? Does it go through the x-axis? But when I solve this quadratic, I'm going to get two answers. But both answers will be imaginary. Okay, both answers will be imaginary. So I can't graph them on this plane. I have to graph them on the complex plane, which we're not going to get into graphing on the complex plane. But when we find two zeros that are imaginary, and we'll talk about what that means next, that tells me that the quadratic, the parabola for that quadratic, never touches the x-axis. It's above the x-axis or below the x-axis, but it never touches. That's why imaginary numbers are important, because we still have to deal with them to find out what the zeros are, what the roots are. And it tells us a lot about what the graph of the parabola looks like. Okay? So getting back to if I find that one of my roots ends up being, and this would happen if I had what? This, right? If I want to solve it, I have to find out what the square root of negative 25 is. Well, right now we don't know how to do that, but after this section you will. Okay, so what mathematicians did is they said, let's break this up into these two parts. Everybody agree that the square root of negative 25 is equal to the square root of 25 times the square root of negative 1. Okay, I know how to do the square root of 25, right? Just 5. Mathematicians said, let's go ahead and just assign this number, the square root of negative 1, we're going to make that the imaginary number I. Okay? Why I don't know. Why they call it imaginary, I don't know. The fact is, the square root of negative 1 is I. Okay? So if I take the square root of 25, I get 5. If I take the square root of negative 1, well, that's just I. So my answer to this problem is plus or minus 5i. Okay? Same would work for square root of negative 49 as an example. Square root of 49 times the square root of negative 1. This is I, so it's just 7i. Okay? Same would work for the square root of negative 18. This is the square root of 18 times the square root of negative 1. Square root of 18 is the square root of 9 times the square root of 2, which is 3 square roots of 2. And then I have an I at the end. All you have to do, if you've got a negative inside, take the square root like you normally do and add an I to the end. Okay? Now, there's something called a complex number, which has two parts. Complex number has a real part and an imaginary part. Okay, an example might be this. How do I get a complex number? Well, what if I had, is that what I want? This problem. Take the square root of both sides. I know this is 2i. Then I have to add 3 to it, right? So I'm going to end up getting x equals 3 plus 2i or 3 minus 2i. This is a complex number. It has a real part and an imaginary part. Okay? If I just have the number 3, I can make that a complex number. There is no imaginary part. So the imaginary coefficient is just 0. If I have a pure imaginary number, I can make that a complex number by putting the real part is 0, imaginary part's 3i. Okay, so complex numbers are always written with a real part first and then the imaginary part second. With me so far? Okay, the last thing I want to talk about, which will come in handy for those of you who are taking the ACT on Saturday. Anybody in here? Okay, there usually is a problem with I on the ACT. Okay, and it might be a problem like this. Evaluate I to the 237th power. What? Okay, I'm going to show you the trick on how to do these. Okay, we know I is the square root of negative 1, right? What is I squared? What's the square root of negative 1 squared?
1, negative 1.
Okay. What's I cubed? It would be I squared times I, right? Everybody know you add exponents when you have the same base? So I cubed is I squared times I. which is just negative I. Negative 1 times I is negative I. With me still? I'm only going to do it one more time. What is I to the fourth? Be careful. It's I squared squared. So what's a negative 1 squared? Negative 1 times negative 1 is just 1. Every number,
So I cubed is I?
negative I. Because you have I squared times I to the first equals I cubed. Right? Because you add exponents when you multiply. Okay? So I squared is negative 1. I is just I. Any number times negative 1 is just negative of that number, right? Negative 1 times 3. Negative 3. Negative 1 times 7. Negative 7. Negative 1 times I. Negative I.
But why is it negative 1 times negative 1?
I cubed?
Yeah.
Because this isn't negative 1.
Yes, it is.
It's the square root of negative 1,
Oh.
which is just what we call I. Okay? You need to know these 4 iterations of I. You need to know them. And if you don't remember them, you need to be able to derive them just like I did. This is how you're going to solve the problem I to the 237th power. Because what you do, if you notice, every 4th iteration of I is just 1. So if I could figure out how many I to the 4ths there are in I to 237, I know all of that goes in evenly to 237. If 4 goes in evenly, every number it goes in evenly to is going to just be 1. And then whatever the remainder is going to be one of those other 3. Let me explain what I'm saying. Before I do this one, let's just do I to the 9th. I to the 9th is I to the 4th times I to the 4th times I to the 1. Right? You add exponents, and that's I to the 9th. Well, I to the 4th is 1 times I to the 4th is 1. So all that's left, I to the 9th is the equivalent of I to the 1st power, because that's the remainder. 4 goes into 9 evenly twice. Those 2 times just goes to 1, and it has a remainder of 1. So 4 goes into 237 how many times evenly? Remainder? So 4 to the I to the 237th is I to the 1st power, which is just I. I to the 201st power. 4 goes into 201 evenly with a remainder of 1. So that's equivalent of I to the 1st power.
So there can be multiple that equal I to the first?
Oh yeah. Every 5th number to infinity. I to the 5th, I to the 9th, and then I to the 13th. Every 5th number, because every one before that's just going to be 1, will be I. Every 6th number will be I squared. Okay, so if you can break your number to an I to the 4th to so many, like this is I to the 4th squared with a remainder of I. I to the 201 is I to the 4th. 4 goes into 250 times to the 50th power times I. Well, this is just 1. I to the 4th is just 1. 1 to the 50th is just 1. So all I have left is just I. Okay? Try I to the 38th power. What will that be? After 4 goes in evenly, how many are left over? Doesn't matter how many times it goes in evenly, but once it goes in evenly, you have 2 left over, right? 36 is where it goes in evenly, 2 left over, so it's I squared, which is -1. Okay, so the problem on the ACT will be something like that. What is this? And your choices will be I, -1, I have no idea. They'll fill in 2 more answers, but it's going to be one of those 3. It could be 1. They might say 1 also. Okay, but that's how you do it, is you know I to the 4th is 1, so if you can take 4 into the exponent, however many times it goes in evenly, take that away, because that'll just be 1. Whatever the remainder is the exponent you raise I to for your answer. Okay? When you're dealing with adding and subtracting complex numbers, it's the same thing that we do when we have any variable. Distribute, combine your like terms, simplify. Okay? So if I distribute this, I can drop the parentheses on the first one, and then I just combine my like terms. That's it. And you always write a complex number with the real portion first, the imaginary portion second. Okay? That's it.